Imagine standing at the edge of oblivion, not merely darkness, but a threshold beyond which the very fabric of existence warps into something unrecognizable. A place where time itself ceases to flow in the manner you've always known, where space curves so violently that even light, the fastest phenomenon in our universe, cannot escape. This is a black hole, and tonight we're going to explore one of the most mind-bending possibilities in all of theoretical physics. What if these cosmic enigmas aren't just gravitational prisons, but gateways to other universes entirely? The question sounds like science fiction, yet it emerges from some of the most rigorously tested theories in modern physics. From the equations of Einstein's general relativity to the strange predictions of quantum mechanics, from the mathematical elegance of string theory to the mind-expanding concepts of eternal inflation, multiple branches of cutting-edge science converge on a startling possibility: the black holes scattered throughout our cosmos. From stellar remnants just a few kilometers across to supermassive giants millions of times more massive than our sun, might connect to realms utterly unlike anything we experience. Parallel universes with different physical laws. Alternate realities where versions of history unfold along divergent paths. Or perhaps older, previous incarnations of our own cosmic story, connected across cycles of time that dwarf our comprehension. Throughout human history, we've been drawn to thresholds and passages. Ancient myths speak of doorways to other worlds, portals to realms of gods and spirits, gateways beyond which the rules of ordinary existence no longer apply. The river Styx, separating life from death. The rainbow bridge, Bifrost, connecting Midgard to Asgard. The looking glass through which Alice tumbled into Wonderland. These stories, passed down through countless generations, reflect something fundamental about human consciousness. We've always sensed that reality might be larger, stranger, and more layered than our immediate perceptions suggest. Modern physics has transformed these intuitions from myth into mathematics. The equations don't speak in metaphors. They speak in precise geometric language about the structure of space-time itself. And what those equations suggest is almost too extraordinary to believe. Yet the mathematics is unambiguous, even if its interpretation remains subject to intense debate among the brightest minds working in theoretical physics today. Black holes were once considered purely theoretical curiosities, mathematical artifacts that couldn't possibly exist in the physical universe. When Carl Schwarzschild found the first exact solution to Einstein's field equations in 1916, just months after general relativity was published, even Einstein himself doubted that such objects could form in nature. The idea seemed too extreme. A region of space where gravity becomes so intense that it creates a boundary from which nothing can return, where all the matter that falls in gets crushed to infinite density at a central point called a singularity. It violated intuition. It seemed to push physics past its breaking point. Yet today, we know black holes are not just real but abundant. The universe is populated with millions upon millions of them. We've detected their gravitational waves rippling through the fabric of space-time when they collide. We've photographed the shadow cast by the supermassive black hole at the center of the galaxy Messier 87, a black hole containing 6.5 billion times the mass of our Sun. We've tracked stars orbiting the supermassive black hole Sagittarius A star at the heart of our own Milky Way galaxy, their paths betraying the presence of an invisible monster with a mass 4 million times that of our Sun. Black holes have transitioned from speculation to confirmed fact, from mathematical possibility to observed reality. And with that confirmation comes new questions. Not whether black holes exist, but what they truly are. What lies beyond that one-way boundary called the event horizon? What happens at the singularity where our equations break down? And most tantalizingly, do black holes connect to something else, somewhere else, some other domain of existence we've barely begun to contemplate? The mathematics suggests they might. When physicists solve the equations of general relativity for black holes, they don't just find a region of space-time that swallows everything that enters. They find structures called Einstein-Rosen bridges, theoretical tunnels through the geometry of the universe itself. They find solutions that don't just end at a singularity, but continue into other regions, other spaces, other possible realities. The equations, quite literally, point toward the possibility of black holes serving as gateways. But the story becomes even stranger when we bring quantum mechanics into the picture. The same mathematics that describes atoms and subatomic particles also makes stunning claims about the nature of reality itself. According to one interpretation that's gaining increasing acceptance among physicists, every quantum event doesn't just have one outcome. Instead, reality branches. The universe splits into multiple versions of itself, and all possible outcomes actually occur in parallel realities that we simply cannot perceive. This is the many worlds interpretation, and it suggests that the multiverse isn't some distant abstraction. It's right here, overlapping with us in every moment, separated by an imperceptible dimensional barrier. Then there's string theory, which requires extra dimensions of space beyond the three we experience. According to this framework, our entire observable universe might exist on something called a brane, a membrane-like structure floating in a higher dimensional space. Other branes, other universe membranes, could exist nearby in dimensions we cannot access. And black holes, which already warp space and time in extreme ways, might create connections between these separate realities. Cosmic inflation, the theory that explains why our universe is so uniform and flat, also points toward a multiverse. When space underwent its initial period of exponential expansion just after the Big Bang, quantum fluctuations should have caused some regions to stop inflating while others continued. The result would be an endless process creating bubble universes throughout an eternally inflating background, like bubbles forming in an infinite ocean of expanding space. Our observable universe would be just one such bubble, surrounded by countless others. Even the concept of the Big Bang itself might need revision. Roger Penrose, the British mathematical physicist who shared the 2020 Nobel Prize in Physics for his work on black holes, has proposed that our universe is just one eon in an infinite cycle of universes. According to his conformal cyclic cosmology, the ending of one universe through its accelerating expansion actually becomes the Big Bang of the next universe. Black holes from the previous eon leave subtle traces in the cosmic microwave background radiation of the current eon, signatures of a universe that existed before our own Big Bang. If Penrose is correct, then the multiverse isn't spread across space or hidden in other dimensions. It's spread across time, with each cycle connecting to the next through a process that involves the evaporation of black holes in the previous universe. All of these ideas, wormholes from general relativity, branching realities from quantum mechanics, extra-dimensional branes from string theory, bubble universes from eternal inflation, and cyclic cosmologies that extend backward and forward through infinite time, converge on a central theme. Our universe is not alone. Reality is far larger than the observable cosmos we can see with our telescopes. And black holes, those most extreme environments where the known laws of physics approach their breaking point, might be the key to understanding and potentially accessing this vaster reality. But we must be careful. Theoretical possibility doesn't equal practical accessibility. The mathematics might allow for black holes to be gateways, but that doesn't mean we could ever traverse one. The forces involved would tear apart any material object long before it reached the event horizon of a stellar mass black hole, in a process colorfully termed spaghettification. Even for supermassive black holes where tidal forces at the horizon are gentler, we face the problem that we could never return to report what we found. And if current theories are correct, the interior of a black hole might not even contain a passageway. The wormhole solution requires conditions that may not exist in real black holes formed from collapsing stars. Yet the theoretical possibility alone revolutionizes our understanding of reality. Even if we can never travel through a black hole to reach another universe, the fact that the mathematics of our most successful physical theories points in this direction tells us something profound. The universe is not a simple, straightforward place. Reality has layers, dimensions, and possibilities that extend far beyond our everyday experience. Black holes, in their very existence, challenge us to expand our conception of what is possible. Let's begin this journey by understanding exactly what black holes are, how they form, and what physics reveals about these cosmic mysteries. Then we'll explore the various pathways through which theoretical physics arrives at the astounding conclusion that black holes might connect to other universes. We'll examine the evidence, the mathematics, the debates, and ultimately confront the profound implications of living in a universe that might be just one reality among countless others. To understand how black holes might serve as gateways to other universes, we first need to understand what black holes actually are. The reality is both simpler and more complex than popular imagination suggests. A black hole is fundamentally a region of space-time where gravity has become so intense that it creates a one-way boundary. This boundary, called the event horizon, marks the surface beyond which the escape velocity exceeds the speed of light. Since nothing can travel faster than light, according to Einstein's special relativity, anything that crosses the event horizon is permanently trapped. Light itself cannot escape, which is why black holes appear black. They don't emit light of their own, and they don't reflect light that falls into them. But calling a black hole a hole is somewhat misleading. It's not an empty void or a tunnel to somewhere else, at least not in any conventional sense. The event horizon isn't a physical surface you could touch. There's no membrane there, no barrier, nothing material marking the boundary. An astronaut falling through the event horizon of a sufficiently large black hole wouldn't feel anything special at that exact moment. From their perspective, space would simply continue, and they would continue falling inward towards something far more mysterious: the singularity. The singularity is where things become truly strange. At this central point, all the matter that has ever fallen into the black hole becomes compressed to infinite density. The curvature of space-time becomes infinite. The mathematical equations of general relativity that accurately describe gravity everywhere else in the universe simply stop working. They produce infinities, meaningless results, a sign that we've reached the limits of our current understanding. This is where quantum gravity, a theory we don't yet have, would be required to describe what actually happens. Black holes form through several different processes, but the most common is stellar collapse. When a massive star exhausts all its nuclear fuel, the outward pressure from fusion reactions suddenly stops. For a black hole to form from stellar collapse, the star's initial mass typically needs to be at least 20 to 25 times that of our Sun, though the exact threshold depends on the star's composition and evolution. Without this pressure to resist gravity, the star's core collapses in on itself catastrophically. The outer layers of the star rebound off the collapsing core, producing a supernova explosion visible across millions of light years. But the core itself continues to collapse, crushing past any state of matter we understand, past neutron degeneracy where atomic nuclei are pressed together into a solid mass of neutrons, until nothing can resist gravity's inward pull. An event horizon forms, and a black hole is born. The Schwarzschild radius defines the size of the event horizon, and it depends only on the mass of the black hole. For our Sun, the Schwarzschild radius is about 3 kilometers. That means, if you could somehow compress the entire Sun, with all its mass, into a sphere just 6 kilometers across, it would become a black hole. For Earth, the Schwarzschild radius is a mere 9 millimeters. These numbers reveal something profound. Any amount of matter can theoretically become a black hole if compressed sufficiently. The universe doesn't prohibit small black holes, but the natural processes we observe typically create black holes with masses several times that of the Sun or larger. Supermassive black holes, the monsters lurking in the centers of galaxies, formed through different mechanisms that we're still working to fully understand. Some may have grown from stellar mass black holes that accreted vast amounts of gas and dust over billions of years. Others might have formed directly from collapsing massive gas clouds in the early universe. Some theories suggest they formed from the merger of many smaller black holes. Regardless of their origin, these giants can contain millions or even billions of solar masses, and their event horizons can span regions larger than our entire solar system. The physics of black holes comes in several varieties, depending on what properties the black hole possesses. The simplest type is the Schwarzschild black hole, named after Karl Schwarzschild. This is a black hole that doesn't rotate and has no electric charge. It's perfectly spherical and characterized entirely by its mass. The geometry of space-time around a Schwarzschild black hole is described by a mathematical solution to Einstein's field equations that Schwarzschild discovered while serving in the German army during World War I. Remarkably, he completed this calculation within a month of Einstein publishing his general theory of relativity. But real black holes in the universe are never quite so simple. They form from rotating stars, so they inherit angular momentum. These rotating black holes are described by a different solution to Einstein's equations, discovered by Roy Kerr in 1963. The Kerr solution reveals that rotating black holes have a more complex structure than Schwarzschild black holes. They possess not one, but two event horizons, an outer and an inner. Between these horizons lies a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. In this region, even standing still is impossible. Space itself is moving, and everything in it must rotate with the black hole. If a black hole also possesses electric charge, the situation becomes even more intricate. The Reissner-Nordström solution describes charged, non-rotating black holes, while the Kerr-Newman solution describes black holes that both rotate and carry charge. These solutions reveal even stranger geometries, with multiple horizons and mathematical structures that hint at connections to other regions of space-time. From the perspective of an outside observer, watching something fall into a black hole reveals one of the theory's most counterintuitive predictions. Time near a black hole flows differently than time far away. This effect, called gravitational time dilation, becomes more extreme the closer you get to the event horizon. An outside observer watching a clock fall toward a black hole would see that clock ticking slower and slower as it approaches the horizon. The light from the falling clock would be redshifted, stretched to longer wavelengths, becoming dimmer and redder. In principle, the clock would appear to take infinite time to actually reach the horizon, its image freezing at the boundary, growing ever dimmer but never quite vanishing completely. This gives some people the impression that nothing actually falls into a black hole, that everything just piles up at the horizon. But this is an illusion of perspective. From the viewpoint of the falling clock or the infalling astronaut, time proceeds normally. They would cross the horizon at a specific moment in their own time frame, experiencing no infinite delay. Once across, they would find themselves in a region from which no escape is possible, not because of some force holding them back, but because the geometry of space-time itself has changed. Inside the event horizon, all paths lead inward toward the singularity. The way forward in time has become the direction toward the center. You can no more avoid reaching the singularity than you can avoid reaching tomorrow. The experience of crossing the event horizon depends dramatically on the size of the black hole. For a stellar mass black hole with a mass just a few times that of the Sun, the tidal forces near the horizon would be lethal. Tidal forces arise from the difference in gravitational pull between your head and your feet. Near a small black hole, this difference becomes extreme. Your feet, slightly closer to the singularity, would experience far stronger gravitational pull than your head. The result is spaghettification, a term physicists actually use. Your body would be stretched lengthwise like a piece of spaghetti while being compressed from the sides. Long before you reach the event horizon, these tidal forces would tear apart your body, then your cells, then your atoms. But for a supermassive black hole, the story changes entirely. The event horizon of a black hole with 1 billion solar masses lies so far from the singularity that the tidal forces at the horizon are actually quite mild. An astronaut could cross this horizon without feeling anything unusual. The killing tidal forces wouldn't arise until much later, when they were deep inside, much closer to the singularity itself. This means that, at least in principle, you could cross the event horizon of a supermassive black hole and remain intact for a while. You would have time to make observations, to experience the bizarre interior of a black hole, before the inevitable encounter with the singularity. What would you see inside? The mathematics suggests something profoundly strange. Inside the event horizon, the singularity is not in front of you in space. It's ahead of you in time. It's your future, unavoidable in the same way that tomorrow is unavoidable. As you fall inward, time and space swap roles in a precise mathematical sense. The radial direction that pointed outward in space has become a direction in time. You're falling toward a when, not just a where. And all around you, light that fell into the black hole before you did is still there, still moving inward. You might see the entire history of the universe playing out in fast forward, all the light that ever fell into this black hole, compressed into your final moments. The details depend on the exact trajectory you followed and the viewing angle, but the general principle holds. Inside a black hole, causality and geometry have transformed into something alien. This interior region, between the event horizon and the singularity, is where the really interesting questions arise. Does it connect to somewhere else? Is there a way through to another region of space-time? Or does everything simply end at the singularity, crushed out of existence in a geometric point where our equations fail? The answer, according to the mathematics, depends on which type of black hole you're considering and how it formed. For a black hole created from a collapsing star, the interior is mostly filled with the stellar material still falling inward. The mathematical solution doesn't have room for wormholes or passages to other universes. The collapse is too messy, too dynamic. Everything converges on the singularity, and that's where the story ends. But if we consider the mathematical solutions themselves, divorced from the question of how black holes actually form in nature, we find something extraordinary. The full, maximally extended solutions to Einstein's equations for black holes contain much more than just a black hole and its interior. They contain white holes, regions of space-time that are the time reverse of black holes. While nothing can escape from a black hole, nothing can enter a white hole. They would expel matter and energy. And connecting the black hole to the white hole in these mathematical solutions is a bridge, a tunnel through space-time itself. This is the Einstein-Rosen bridge, named after Einstein and his colleague Nathan Rosen, who first described it in 1935. Today we call such structures wormholes. The question that has fascinated physicists for decades is whether these wormholes are merely mathematical curiosities, or whether they might exist in the physical universe. And if they exist, could they provide passages to other regions of space-time? Could a black hole in our universe connect to a white hole elsewhere, perhaps in a different universe entirely? This is where our journey into the multiverse truly begins. In July 1935, just 2 decades after Einstein published his general theory of relativity, he and his assistant, Nathan Rosen, published a peculiar paper. They weren't trying to discover wormholes or gateways to other universes. Their goal was more modest and, in their view, more practical. They wanted to find a way to describe elementary particles, like electrons, without having point-like singularities where physical quantities became infinite. Singularities bothered Einstein. They suggested that the theory was incomplete, that something was missing from the equations. Working with Einstein's field equations, they found a mathematical solution that seemed to offer a way forward. When they analyzed the geometry around what we now call a Schwarzschild black hole, they discovered that the solution could be extended. It didn't just describe a single region of spacetime with a black hole in it. Instead, it connected 2 separate regions of flat spacetime through a bridge. Picture 2 universes, or 2 distant parts of the same universe, each containing ordinary space extending to infinity. Now imagine these 2 spaces connected by a tunnel, whose entrance is the event horizon of a black hole in one space, and whose exit is a white hole in the other. This Einstein-Rosen bridge wasn't a physical object in the conventional sense. It was a purely geometric feature, a property of how spacetime could be curved according to general relativity. The bridge connected 2 different regions, but in the original solution, it had a fatal flaw. It wasn't traversable. The throat of the wormhole, the narrowest part of the tunnel, would pinch off and collapse faster than light could travel through it. Anything trying to pass from one side to the other would be trapped in the collapsing throat and crushed. The bridge existed mathematically, but it couldn't be used as a passage. For decades, this remained an interesting but seemingly impractical curiosity. The equations allowed these structures, but they appeared irrelevant to the physical universe. Real black holes formed from collapsing stars wouldn't have these bridges. The collapsing matter filled the interior, preventing the formation of any passage to another region. Einstein-Rosen bridges seemed destined to remain mathematical artifacts without physical significance. Then, in the mid-1980s, the situation changed. Carl Sagan, the famous astronomer and science communicator, was writing his novel, Contact, which featured a character traveling through a wormhole to reach a distant star. Sagan wanted the story to be as scientifically accurate as possible, so he approached Kip Thorne, a theoretical physicist at Caltech who specialized in general relativity and black holes. The question he posed was simple. Could you design a wormhole that would actually work for interstellar travel? Thorne took the challenge seriously. Working with his graduate students Michael Morris and Ulvi Yurtsever, he set out to determine whether the laws of physics permitted traversable wormholes. They approached the problem differently than anyone before. Instead of starting with black hole solutions and looking for bridges, they began by specifying what they wanted: a wormhole that remained open, long enough for something to pass through, with tidal forces gentle enough that a traveler could survive. Then they asked, what kind of matter and energy would be required to create and maintain such a structure? The answer they found was simultaneously encouraging and problematic. Yes, the equations of general relativity do allow traversable wormholes to exist. The geometry works, but maintaining such a wormhole requires something that has never been observed in nature: exotic matter with negative energy density. In ordinary matter, energy density is positive. The presence of mass and energy causes space-time to curve inward, producing attractive gravity. But to hold a wormhole open, you need matter that causes space-time to curve outward, producing a kind of repulsive gravity. This requires negative energy density, an energy content less than the vacuum of empty space itself. Quantum field theory suggests that such negative energy densities might be possible, at least temporarily and in tiny amounts. The vacuum of space isn't truly empty. Virtual particles constantly pop in and out of existence, fluctuations permitted by Heisenberg's uncertainty principle. Under special circumstances, these quantum effects can produce regions where the energy density is slightly negative compared to the surrounding vacuum. The Casimir effect, experimentally verified in laboratory conditions, demonstrates this principle. Two parallel metal plates, placed extremely close together, experience an attractive force because certain wavelengths of virtual particles are excluded from the gap between the plates, creating a region of negative energy density compared to the surrounding space. But the amount of negative energy produced by the Casimir effect or similar quantum phenomena is minuscule, far below what would be needed to hold open a macroscopic wormhole. To create a traversable wormhole large enough for even a single atom to pass through would require concentrations of negative energy that dwarf anything we can currently produce, or even theoretically imagine producing. And the wormhole would need to be actively maintained. Any disruption, any influx of ordinary positive energy matter would cause the structure to collapse. This hasn't stopped physicists from exploring the concept further. If exotic matter with negative energy could somehow be obtained or created, then general relativity tells us exactly how to use it. The throat of the wormhole would need to be threaded with this exotic matter in a very specific configuration. The negative energy would push outward against gravity's tendency to collapse the structure, keeping the passage open. In principle, you could then travel through the wormhole from one end to the other, experiencing neither infinite crushing forces nor infinite time delays. The journey would be brief, perhaps almost instantaneous from the traveler's perspective, depending on the length of the tunnel. The geometry of these traversable wormholes has been extensively studied using tools like Penrose diagrams. Roger Penrose, the British mathematical physicist, developed these diagrams to represent the causal structure of curved spacetime in a way that makes it easier to visualize and analyze. In a Penrose diagram, light rays always travel at 45-degree angles, regardless of the spacetime curvature. This allows physicists to quickly determine which events can influence which other events, which regions are causally connected, and where horizons and singularities appear. When you draw a Penrose diagram for the maximally extended Schwarzschild solution, the complete mathematical structure Einstein-Rosen originally studied, you get something remarkable. The diagram reveals 4 distinct regions. There's the exterior universe where we live, containing stars and galaxies extending to infinity. There's the interior of the black hole, the region behind the event horizon, leading to the singularity. But there's also another exterior region, a second universe, or a distant part of our own universe, completely separate from our observable cosmos. And finally, there's the interior of a white hole, the time-reversed counterpart to the black hole, where matter and light can only exit, never enter. These 4 regions are connected in a specific way. The black hole interior and white hole interior meet at the singularity, but this singularity is time-like rather than space-like, meaning it appears as a vertical line in the Penrose diagram rather than a horizontal boundary. The 2 exterior regions are connected through the Einstein-Rosen bridge, which passes through the interiors. In principle, you could enter the black hole from our universe, pass through the bridge, and emerge from the white hole into the other exterior region. But there's a catch. The geometry of the Schwarzschild solution doesn't allow you to actually make this journey. The bridge pinches off too quickly. By the time you cross the event horizon, the throat has already collapsed, and all paths lead to the singularity. For rotating black holes, described by the Kerr solution, the situation becomes even more intricate. The Kerr geometry has an inner and outer event horizon, and the singularity is ring-shaped rather than point-like. If you could somehow approach the ring singularity along its axis, the mathematics suggests you might pass through the ring without hitting it, emerging into a region of negative mass and strange causality where closed time-like curves, paths that loop back on themselves in time, become possible. Beyond this lies yet another, asymptotically flat region, potentially another universe. But all of these exotic features come with enormous caveats. The Kerr solution, like the Schwarzschild solution, is eternal and unchanging. It's existed forever in the past and will exist forever in the future. Real black holes form from collapsing stars at specific moments in time. When you account for the formation process, the additional regions largely disappear. The collapsing stellar matter fills the interior, and there's no longer any passage to another region. The wormhole throat never opens. This leads to a crucial distinction. The mathematical solutions to Einstein's equations contain these elaborate structures, but that doesn't mean physical black holes possess them. It's similar to how the equation x squared equals 4 has two solutions, +2 and -2. But if you're calculating the radius of a circle with area 4pi, only the positive solution has physical meaning. The negative radius isn't relevant to the real problem. In the same way, the additional regions of the maximally extended black hole solutions might be mathematical features that don't correspond to anything in the physical universe. Yet the possibility tantalized physicists. If the equations allow wormholes to exist, even under very special and probably unrealistic conditions, then understanding these solutions might reveal something deep about the structure of space-time itself. Even if we can never travel through a wormhole, the fact that the mathematics includes them suggests that space-time has more flexibility, more potential for exotic structures than we might otherwise imagine. And this opened a door to thinking about black holes in new ways, not just as objects that swallow matter and energy, but as potential connectors, bridges, gateways in the fundamental fabric of reality. This way of thinking gained additional support from an unexpected direction: quantum mechanics and quantum information theory. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a startling connection between quantum entanglement and wormholes. Quantum entanglement is a phenomenon where two particles become correlated in such a way that measuring one instantly determines the state of the other, regardless of the distance between them. Einstein called this spooky action at a distance and found it deeply troubling. Maldacena and Susskind suggested that quantum entanglement and Einstein-Rosen bridges might be two different descriptions of the same underlying phenomenon. Their conjecture, known as ER equals EPR, where ER stands for Einstein-Rosen and EPR stands for Einstein-Podolsky-Rosen, the authors of the paper that first described quantum entanglement, proposed that every pair of entangled particles is connected by a tiny wormhole. The entanglement isn't action at a distance through empty space. It's a connection through a miniature bridge in space-time itself. If this connection is correct, it would be profound. Quantum entanglement is ubiquitous in the universe. Every quantum interaction produces entangled particles. This would mean that space-time is laced with countless microscopic wormholes, a foamy structure at the quantum level where space is constantly connecting to itself in ways we can't directly perceive. And if black holes are entangled with the Hawking radiation they emit, as quantum mechanics suggests they must be, then these wormholes might play a crucial role in understanding how information escapes from black holes, resolving one of the deepest paradoxes in theoretical physics. The mathematics of wormholes, originally discovered as a curious feature of Einstein's equations, has evolved into a rich field studying the connections between gravity and quantum mechanics, between geometry and information, between the large-scale structure of space-time and the microscopic world of particles and fields. Whether actual, traversable wormholes exist in our universe remains unknown, but the concept has proven invaluable for exploring the limits of physical law and imagining what lies beyond those limits. While general relativity deals with the large-scale curvature of space-time, quantum mechanics governs the microscopic realm of atoms and subatomic particles. And quantum mechanics makes claims about reality that are, if anything, even stranger than the warped geometry of black holes. Among the strangest is the many worlds interpretation, which suggests that we live in a multiverse not because of extra dimensions or distant bubble universes, but because reality itself branches and splits with every quantum event. The story begins with the measurement problem in quantum mechanics. According to the theory's fundamental equations, particles don't have definite properties until they're measured. Before measurement, a particle exists in what's called a superposition, a quantum state that combines multiple possibilities simultaneously. An electron doesn't have a specific location before you observe it. Instead, it exists as a wave function that spreads across space, describing probabilities for finding it at different locations. Only when you make a measurement does the wave function collapse, forcing the particle to assume one definite state. This wave function collapse has troubled physicists since the birth of quantum mechanics in the 1920s. The mathematics describes the evolution of quantum systems with exquisite precision, predicting experimental results with incredible accuracy. But the equations that govern this evolution are deterministic and reversible. They describe smooth, continuous changes in the wave function over time. Then suddenly, at the moment of measurement, something different happens. The wave function collapses discontinuously, instantly, seemingly in violation of the very equations that describe quantum evolution. It's as if the universe has two completely different sets of rules, one for when nobody's looking, and another for when we make measurements. What counts as a measurement? Does it require a conscious observer? Does it require a sophisticated measuring device? Or does any interaction with the environment count as measurement? These questions plagued quantum mechanics for decades. Different physicists proposed different interpretations, different ways of understanding what the mathematics was really saying about the nature of reality. The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, suggested that we shouldn't ask what's really happening before measurement. The wave function is just a tool for calculating probabilities, not a description of physical reality. Only measurement outcomes are real. But in 1957, a graduate student at Princeton named Hugh Everett proposed a radical alternative. What if the wave function never collapses? What if the apparent collapse is just an illusion created by our perspective? Everett's insight was deceptively simple. The standard quantum equations, the ones that describe smooth, reversible evolution, don't just apply to particles. They apply to everything, including measuring devices and observers. When you make a measurement, you don't cause the wave function to collapse. Instead, you become entangled with the system you're measuring. Imagine measuring the spin of an electron, a quantum property that can be either up or down. Before measurement, the electron exists in a superposition of both states simultaneously. According to the Copenhagen interpretation, the act of measurement forces the electron to choose one state, and the wave function collapses. According to Everett's interpretation, something very different happens. The measuring device, initially in a ready-to-measure state, becomes entangled with the electron. The combined system evolves into a superposition of two possibilities, one where the device measured spin up and one where it measured spin down. But here's the crucial part. You, the observer, are also part of the quantum system. When you look at the measuring device, you become entangled with it. The wave function now describes a superposition containing two versions of you, one who saw spin up and one who saw spin down. Both versions exist. Both are equally real, but they can no longer interact with each other. They've decohered, branched into separate worlds. Each version of you experiences a universe where the measurement had one definite outcome. From your perspective inside one branch, the wave function appears to have collapsed. But objectively, both outcomes occurred, and reality split into parallel branches. This is the many worlds interpretation. Every quantum measurement doesn't select one outcome from many possibilities. Instead, it creates new branches of reality where every possible outcome actually happens. The universe is constantly splitting, differentiating, branching into inconceivably vast numbers of parallel realities. And this isn't some distant process happening in other dimensions. It's happening right here, right now, in every quantum interaction throughout the cosmos. There are countless versions of you reading these words, separated by quantum branches that occurred microseconds ago. In some branches, you decided to stop reading. In others, you've already finished. In still others, you never started. The many worlds interpretation was initially dismissed by most physicists as too extravagant, too philosophically troubling. Bohr never took it seriously. Even Einstein, who criticized the Copenhagen interpretation on other grounds, didn't endorse Everett's alternative. The idea of the universe constantly splitting into parallel realities seemed like multiplying entities far beyond necessity. But over the decades, the interpretation gained respectability and adherence. Several factors contributed to this shift. First, the many worlds interpretation is mathematically simpler than the Copenhagen interpretation. It doesn't require adding extra rules to describe wave function collapse. The standard Schrödinger equation, applied universally to everything, explains all observations without modification. From a theoretical elegance standpoint, this is appealing. Why should we add a collapse postulate to the theory if we can explain everything without it? Second, the interpretation makes predictions that differ from Copenhagen in subtle ways, particularly regarding quantum computing and quantum information. In the many worlds framework, quantum computers work by exploring all possible computational paths in parallel across different branches of reality. The final measurement collapses these branches from our perspective, but the computation actually occurred across the multiverse. This provides a natural explanation for why quantum computers can solve certain problems exponentially faster than classical computers. They're not just processing information more cleverly within a single universe. They're harnessing computational resources from parallel realities. Third, the development of quantum decoherence theory in the 1980s and 1990s explained how branches form and why we don't perceive quantum superpositions at macroscopic scales. Decoherence occurs when a quantum system interacts with its environment. These interactions cause the different components of a superposition to lose their quantum coherence, their ability to interfere with each other. Once decoherence occurs, the branches become effectively separate, even though they're all still part of the same universal wave function. This explains why we never see cats that are simultaneously alive and dead, why quantum weirdness seems confined to the microscopic realm. It's not that quantum mechanics stops applying at large scales. It's that decoherence happens so rapidly for large objects that the branches separate almost instantly. The physicist David Deutsch, one of the founders of quantum computing theory, has been a particularly strong advocate for the many worlds interpretation. Deutsch argues that quantum computing only makes sense in a many worlds framework. When a quantum computer factors a large number using Shor's algorithm, it's not finding the answer through some clever single-world process. It's distributing the calculation across exponentially many parallel realities, each exploring a different potential factor. The interference patterns in the quantum circuit that ultimately produce the correct answer are interference between these parallel computations. From Deutsch's perspective, denying the existence of parallel universes while accepting that quantum computers work is logically inconsistent. But the many worlds interpretation also faces serious conceptual challenges. If every possible outcome occurs, what does probability mean? In a single universe interpretation, the wave function gives us probabilities for different outcomes, and one outcome actually happens. In many worlds, all outcomes happen. So why do we experience the illusion of probability? Why does a quantum coin flip that's 90% likely to be heads and 10% likely to be tails appear to give heads more often if both outcomes always occur? Everett and his successors have proposed various answers. The most common approach uses the idea of measure. Even though all branches exist, they don't all have equal weight or amplitude. The squared amplitude of the wave function, which in the Copenhagen interpretation gives us probabilities, in many worlds determines the relative measure or thickness of different branches. When you experience a measurement outcome, you should think of yourself as being randomly sampled from the multiverse according to this measure. You're more likely to find yourself in thicker branches than thinner ones, which recreates the appearance of quantum probability. This answer satisfies some physicists, but leaves others unconvinced. How can you apply probability to a deterministic theory where everything happens? The debate continues, with philosophers and physicists proposing increasingly sophisticated approaches to the probability question. But regardless of these conceptual challenges, the many worlds interpretation remains one of the leading contenders for understanding quantum mechanics. Now, what does all this have to do with black holes? The connection comes through several pathways. First, if many worlds is correct, then every black hole exists in superposition across countless branches. In some branches, specific stars collapse to form the black hole. In others, different stars or configurations of matter created it. The black hole we observe is just one branch of an incomprehensibly vast tree of possibilities. Each branch contains a slightly different black hole, and all these branches are equally real parts of the quantum multiverse. Second, when matter falls into a black hole, it carries quantum information. According to quantum mechanics, information cannot be destroyed, but black holes appear to destroy information by crushing it at the singularity. This information paradox, which we'll explore in depth shortly, becomes even more acute in a many worlds framework. If information can't be destroyed in any branch, and if all branches exist, then what happens to the quantum information that falls into black holes across countless parallel realities? Third, the many worlds interpretation suggests that quantum branching might be fundamental to space-time structure itself. Some physicists have proposed that space-time is not a smooth, continuous fabric, but emerges from quantum entanglement patterns at the most fundamental level. In this view, the connectivity of space, the fact that nearby points in space can influence each other, arises from quantum correlations. And if quantum correlations create branches, then perhaps the multiverse structure isn't separate from space-time. Perhaps the many worlds are woven into the very geometry that general relativity describes. This leads to a stunning possibility. What if black holes, which already warp space-time in extreme ways, also warp the branching structure of quantum reality? What if crossing the event horizon doesn't just take you to a different region of space, but to a different branch of the multiverse? The interior of a black hole might be a region where quantum branches reconnect, or where the branching structure itself has different topology. From this perspective, black holes might serve as gateways, not because they contain wormholes in the general relativistic sense, but because they represent locations where the quantum multiverse has unusual structure. These ideas remain highly speculative at the frontiers of theoretical physics, where quantum mechanics and general relativity intersect. But they illustrate how the many worlds interpretation naturally connects to questions about black holes and the multiverse. If reality constantly branches, and if black holes represent extreme environments where our usual physical understanding breaks down, then the interiors of black holes become natural candidates for places where we might access other branches, other worlds, other versions of reality. The many worlds interpretation thus provides one pathway to a multiverse, one that doesn't require extra dimensions or inflation or cyclic cosmologies. The parallel universes are right here, overlapping with ours, separated only by quantum decoherence. And black holes, those most mysterious objects in our universe, might be places where the veil between worlds becomes thin, where the structure of reality itself takes on forms we can barely imagine. In 1974, Stephen Hawking made a discovery that shocked the physics community. Black holes, long thought to be perfectly black, actually emit radiation. They glow with a faint thermal radiation that causes them to slowly evaporate over time. This discovery, now called Hawking radiation, fundamentally changed our understanding of black holes and created a paradox that has driven theoretical physics research for 5 decades. Hawking's calculation combined quantum field theory with general relativity in a new way. He considered how quantum fields behave in the curved space-time near a black hole's event horizon. In quantum field theory, the vacuum isn't truly empty. Virtual particle-antiparticle pairs constantly pop into existence and annihilate each other, fluctuations permitted by Heisenberg's uncertainty principle. Normally, these virtual pairs exist for such brief moments that they have no measurable effect. But near an event horizon, something remarkable can happen. Imagine a virtual particle pair appearing just outside the event horizon. In flat space-time, the pair would annihilate almost immediately, but near a black hole, the intense gravitational field can separate the pair before annihilation occurs. One particle falls into the black hole while its partner escapes to infinity. To a distant observer, it appears that the black hole has emitted a particle. This process happens continuously all around the event horizon, producing a steady stream of radiation. The energy for this radiation must come from somewhere. It comes from the black hole itself. Each time a particle escapes, the black hole loses a tiny amount of mass through Einstein's famous equation, equals mc squared. The black hole is evaporating, converting its mass into radiation. For stellar mass black holes, this evaporation is extraordinarily slow. A black hole with the mass of the Sun would take roughly 10 to the 67th power years to evaporate completely, far longer than the current age of the universe. But the smaller the black hole, the faster it evaporates. A black hole with the mass of a mountain would evaporate in seconds, releasing its energy in a tremendous explosion. The radiation has a characteristic temperature inversely proportional to the black hole's mass. Stellar mass black holes have temperatures just a fraction above absolute zero, far colder than the cosmic microwave background radiation that fills space. They actually absorb more radiation from their surroundings than they emit, so they grow rather than shrink. But in the far future, when the universe has expanded and cooled sufficiently, even these massive black holes will begin their long evaporation. Supermassive black holes would take incomprehensibly longer, requiring something like 10 to the 100th power years to vanish completely. The temperature calculation revealed something profound. Black holes have thermodynamic properties. They have temperature. They have entropy, a measure of disorder and information content. The entropy of a black hole, calculated by Jacob Bekenstein shortly before Hawking discovered his radiation, is proportional to the area of its event horizon, not its volume. This was strange and unexpected. For ordinary objects, entropy is proportional to volume, to the number of particles or atoms they contain. But black holes are different. All their entropy is somehow encoded on their surface, on the 2-dimensional event horizon, not in the 3-dimensional interior. This area law for entropy became a key clue leading to the holographic principle, which we'll explore later. But first, it created a severe problem, the information paradox. When matter falls into a black hole, it carries information. This information includes quantum information. the complete specification of its quantum state. According to the fundamental principles of quantum mechanics, information can never be destroyed. Quantum evolution is unitary, reversible. You can always, in principle, reconstruct the past from the present if you know the quantum state precisely enough. But what happens to information when it falls into a black hole, and the black hole then evaporates through Hawking radiation? The radiation Hawking calculated is purely thermal. It has the spectrum of a perfect blackbody, completely random, containing no information about what fell into the black hole. It's like burning an encyclopedia and analyzing the smoke. The smoke is hot gas with a thermal spectrum. It doesn't contain any of the information that was in the encyclopedia. The information has been destroyed. This contradicts quantum mechanics. If quantum mechanics is correct, information cannot be destroyed. It must be preserved somehow. Either the information remains inside the black hole until the very end of evaporation, then emerges in the final burst of radiation, or it escapes gradually throughout the evaporation process, encoded somehow in subtle correlations within the radiation that Hawking's calculation missed. Or quantum mechanics is wrong, and information can be destroyed, but this would require revising the most successful theory in the history of physics. Hawking himself initially argued that information is destroyed, that black holes represent an exception to quantum mechanics. This was a bold claim, suggesting that general relativity takes precedence over quantum mechanics in this extreme situation. But most physicists were unwilling to accept information destruction. The debate raged for decades, with no clear resolution. The information paradox became one of the deepest problems in theoretical physics, touching on the most fundamental questions about the nature of reality. Several proposed solutions emerged. One suggestion involved black hole remnants. Perhaps black holes don't completely evaporate. When they get small enough, maybe quantum gravity effects halt the evaporation, leaving behind a tiny stable remnant that contains all the information that fell in. But calculations suggested these remnants would need to have enormous internal entropy, far more states than any object so small should possess. They would be like having infinite information packed into a finite volume, which seems problematic. Another proposal involved baby universes. Perhaps the information falling into a black hole doesn't get destroyed or remain in our universe. Instead, it goes somewhere else. The black hole interior might bud off, forming a separate baby universe disconnected from our own. The information would still exist, preserving unitarity, but it would be permanently inaccessible to us. This solution saves quantum mechanics, but at the cost of losing predictability. If information can leave our universe, we can never use quantum mechanics to make complete predictions about the future. The most dramatic proposal came from string theorists in the late 1990s. They suggested that the event horizon isn't smooth and empty. Instead, it's surrounded by a firewall, a region of extreme high-energy particles that would incinerate anything attempting to cross it. This firewall would form due to quantum effects once the black hole had evaporated enough to threaten information loss. The firewall prevents information from truly entering the black hole, preserving unitarity. But it also contradicts one of the fundamental principles of general relativity, the equivalence principle, which states that freely falling observers shouldn't experience anything special at the event horizon. The firewall proposal sparked intense debate. It seemed to present a stark choice: either preserve quantum mechanics and violate general relativity with a firewall, or preserve general relativity and accept information destruction. Neither option was attractive. Physicists scrambled to find alternatives that could preserve both theories, or to determine which theory should take precedence. Then, in the 2010s, progress began emerging from the holographic principle and the ADS/CFT correspondence, tools from string theory that suggested information does escape, but in a subtle way. The key insight was that the Hawking radiation isn't as independent and thermal as Hawking's original calculation suggested. When you account for quantum entanglement carefully, the radiation particles emitted early in the evaporation process are entangled with particles emitted later. These correlations encode information about what fell into the black hole. The information escapes gradually, scrambled and encoded in patterns of quantum entanglement that span the entire radiation output. Detailed calculations showed that for most of the black hole's lifetime, the radiation appears thermal and information-free, just as Hawking calculated. But at a specific point, called the page time, roughly halfway through the evaporation process, the information content of the escaped radiation begins to exceed the information remaining in the black hole. After this point, information increasingly resides in the radiation rather than the black hole. By the time the black hole completely evaporates, all the information has escaped, preserved in the correlations within the radiation. This resolution requires modifying our picture of space-time inside and around black holes. The interior isn't as simple as general relativity suggests. Quantum effects create connections between the interior and the emitted radiation, connections that become stronger as evaporation proceeds. These connections might be tiny wormholes, quantum entanglement bridges that link the black hole to distant radiation particles that escaped long ago. In this picture, the black hole interior and the Hawking radiation aren't separate. They're quantum mechanically connected, entangled in ways that preserve information while still appearing locally, like Hawking's thermal radiation. In 2019 and 2020, calculations by Ahmed Almheri, Thomas Hartman, Juan Maldacena, Edgar Shaghulian, and Amir Hossein Tajdini provided strong evidence for this resolution. Their work showed that when you carefully account for quantum gravity effects using tools from string theory, information does escape, and the paradox can be resolved without firewalls or information destruction. However, these calculations required assuming that gravity is fundamentally holographic, that the physics of black holes can be completely described by a quantum theory living on a boundary far from the black hole itself. This brings us to a crucial point for our exploration of black holes as gateways. The resolution of the information paradox suggests that black hole interiors are quantum mechanically connected to distant regions of space-time through entanglement and holography. The interior isn't an isolated region cut off from the outside universe. It's intimately connected to the Hawking radiation, which spreads throughout space as the black hole evaporates. These connections, these quantum bridges, might be tiny wormholes, Einstein-Rosen bridges at the quantum scale. If this picture is correct, then black holes already serve as a kind of gateway, not to other universes in the sense of completely separate realities, but to distant regions of our own universe through quantum entanglement structures. The interior of a black hole might be less like a pit and more like a quantum network hub, connected to countless other locations through the radiation it has emitted over its lifetime. And if these quantum connections can link a black hole to distant parts of our universe, perhaps similar connections could link black holes to other universes in a larger multiverse. The information paradox and its resolution thus provide another piece of the puzzle. Black holes aren't just objects described by general relativity. They're quantum objects with properties that emerge from deep connections between gravity, quantum mechanics, and information. And these properties hint at structures, connections through spacetime, and perhaps between different spacetimes, that we're only beginning to understand. Everything we've discussed so far has operated within the framework of 4 dimensions, 3 of space and 1 of time. But what if reality contains more dimensions than we perceive? What if our entire universe exists on a membrane floating in a higher dimensional space? These ideas come from string theory, one of the most ambitious attempts to unify quantum mechanics and general relativity into a single framework. String theory proposes that the fundamental constituents of reality aren't point-like particles but tiny one-dimensional strings. These strings vibrate, and different vibration patterns correspond to different particles. An electron is one vibration pattern, a quark is another, a photon is a third. The theory elegantly unifies all particles and forces, including gravity, into a single mathematical structure. But this unification comes with a price. The mathematics only works if spacetime has more than 4 dimensions. The original version of string theory required 10 dimensions total, 9 of space and 1 of time. Later versions, incorporating supersymmetry and other features, sometimes require 11 dimensions. Where are these extra dimensions? Why don't we perceive them? The standard answer invokes compactification. The extra dimensions are curled up into shapes so small that we cannot detect them directly. At every point in the 3-dimensional space we observe, 6 or 7 additional spatial dimensions extend in directions perpendicular to all 3 directions we know. But these extra dimensions are compactified into geometric shapes with sizes around the Planck length, roughly 10 to the negative 35 meters. This might sound absurd, but there's a useful analogy. Imagine looking at a garden hose from a distance. It appears one-dimensional, a line. But if you zoom in, you discover the hose has width, a second dimension that was invisible from far away. The surface of the hose is actually 2-dimensional, but one dimension is compactified into a tiny circle that wraps around the hose. String theory suggests something similar happens with our universe. We perceive 3 dimensions because they're large and extended. The extra dimensions are compactified, curled up so small that we've never detected them, even with our most powerful particle accelerators. The geometry of these compactified dimensions matters enormously. Different shapes, called Calabi-Yau manifolds, produce different physics in the observable dimensions. The masses of particles, the strengths of forces, even the number of particle generations we observe, all depend on the precise shape of the compactified dimensions. String theory doesn't predict a unique geometry. There are many possible ways to compactify the extra dimensions, perhaps 10 to the 500 different configurations or more. Each configuration corresponds to a different possible universe with different physical laws. This led to the string theory landscape, a vast space of possible universes, all described by string theory, but with different low-energy physics. Some of these universes would have electrons and quarks like ours. Others might have completely different particles. Some would have 4 fundamental forces. Others might have more or fewer. The constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, would vary from universe to universe across the landscape. In the late 1990s, physicists exploring string theory made another remarkable discovery. The theory naturally contains higher dimensional objects called branes. 0-dimensional branes are points. 1-dimensional branes are strings, the fundamental objects that gave the theory its name. But there are also 2-dimensional membranes, 3-dimensional volumes, and higher dimensional structures, up to 9-dimensional branes in some versions of the theory. These branes aren't just mathematical curiosities. They're physical objects, where strings can end. An open string has 2 endpoints, and these endpoints must lie on branes. Moreover, certain particles and forces are confined to branes. A 3-dimensional brane, for instance, could trap electromagnetic fields and matter particles while gravity propagates freely through all dimensions, including the bulk space between branes. This led Lisa Randall and Raman Sundram to propose a radical idea in 1999. What if our entire universe is a 3-dimensional brane floating in a higher dimensional space? Everything we observe, all the matter and energy, all the forces except gravity, would be confined to our brain. We couldn't leave it or detect anything outside it directly because we're fundamentally attached to it. Like characters drawn on a sheet of paper, who cannot perceive the third dimension perpendicular to their page. This brain world scenario immediately suggests the possibility of parallel universes. If our universe is a brain, why couldn't there be other brains floating nearby in the bulk? These other brains would be complete universes in their own right, with their own matter, their own stars and galaxies, their own physical laws determined by the geometry of the extra dimensions at their location. Two brains could be separated by less than a millimeter in the extra dimensions, yet completely invisible to each other because light cannot travel through the bulk. However, gravity is different. In these models, gravity propagates through all dimensions, including the bulk. This means that brains can gravitationally influence each other, even though they're otherwise invisible. The dark matter we observe in our universe, the mysterious substance that outweighs visible matter by 5 to 1, might actually be ordinary matter on a nearby brain. We can't see it because light is confined to our brain, but we feel its gravitational pull because gravity extends through the bulk. Some brain cosmology models go further, suggesting that the Big Bang wasn't the beginning of time, but rather a collision between brains. In the ekpyrotic universe model, developed by Paul Steinhardt and Neil Turok, the universe undergoes cycles. Two brains exist in the bulk, separated by a small gap. They're attracted to each other through bulk forces, slowly approaching over billions of years. When they collide, the kinetic energy of the collision converts into matter and radiation on both brains. Each collision appears from the perspective of beings on the brains like a Big Bang, a sudden beginning filled with hot, dense energy that expands and cools. After the collision, the brains bounce apart, separate, and begin approaching again. The cycle repeats eternally. The cosmic microwave background radiation that we observe as the afterglow of the Big Bang would, in this model, be the afterglow of the most recent brain collision. And the expansion we observe would be the brains moving apart after their collision. In some versions of this cyclic model, dark energy, the mysterious force accelerating cosmic expansion, provides the mechanism that pulls the brains back together for the next collision. These brain cosmology scenarios provide yet another pathway to a multiverse. The other brains aren't distant or inaccessible. They're right here, in some sense, separated only by a small distance in extra dimensions that we cannot perceive. And black holes, which already warp the usual 3 spatial dimensions dramatically, might warp the extra dimensions as well. A black hole's singularity, where space-time curvature becomes infinite, might extend through all dimensions, connecting our brain to other brains in the bulk. Some string theorists have speculated that black holes could serve as bridges between brains. If a black hole forms on one brain and its gravitational field extends through the bulk, it might connect to a corresponding structure on another brain. Matter falling into the black hole on our brain could emerge from a white hole on the other brain. The Einstein-Rosen bridge, which didn't work in standard 4-dimensional general relativity due to collapse, might be stabilized by the extra dimensions and the tension of the brains themselves. There's even a possible connection to dark energy. In brain cosmology, the energy density of the vacuum on our brain depends on the separation between brains and the curvature of the bulk. As the configuration of brains in the bulk evolves, the vacuum energy on each brain changes. This could explain why dark energy has the particular value we observe, so small that it only became important in recent cosmic history. The brain separation might have reached a critical value that produces our observed dark energy density. Testing these ideas experimentally is challenging. The extra dimensions are presumably too small to detect directly, but there are indirect signatures we might look for. If gravity propagates through extra dimensions, it should behave differently at very short distances. Experiments have tested Newton's inverse square law of gravity down to distances of around 50 micrometers, looking for deviations that would indicate extra dimensions. So far, they've found none. but the tests continue to improve. Another signature would be mini black holes created at particle colliders. If extra dimensions exist and are large enough, the Large Hadron Collider might create tiny black holes when particles collide at high energies. These black holes would evaporate almost instantly through Hawking radiation, but their characteristic signature would be detectable. Despite searches, no evidence for such black holes has been found, which places constraints on extra-dimensional models. Gravitational waves provide another testing ground. When black holes merge, they send ripples through space-time that we can detect with instruments like Virgo. If extra dimensions exist, gravitational waves might leak into the bulk, carrying away energy that we wouldn't detect. Or they might leave imprints in the wave pattern that reveal extra-dimensional structure. Current observations match the predictions of standard four-dimensional general relativity very well. But as measurements become more precise, subtle extra-dimensional effects might appear. The connection between string theory, extra dimensions, and black holes as gateways remains theoretical but mathematically rich. String theory suggests that our universe might be just one brane among many, floating in a higher dimensional space. Black holes, which already represent regions where space-time becomes extremely warped, might warp the extra dimensions as well, potentially creating connections to other branes, other universes. The mathematics allows these possibilities, even if experimental confirmation remains beyond our current reach. One of the strangest ideas to emerge from the study of black holes is the holographic principle, which suggests that our three-dimensional reality might actually be a projection from information encoded on a two-dimensional surface. This concept revolutionized how physicists think about black holes, quantum gravity, and potentially the nature of the universe itself. The story begins with black hole entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking calculated that black holes have entropy proportional to the area of their event horizon, not their volume. This was puzzling. For normal objects, entropy counts the number of possible microscopic states, which typically scales with the number of particles, hence with volume. A box twice as large contains twice as many particles and roughly twice as much entropy. But black holes don't follow this pattern. AA black hole's mass, and its volume increases by a factor of 8, but its entropy only increases by a factor of 4, following the surface area. This area law suggested something deep. Gerard 't Hooft and Leonard Susskind, working independently in the 1990s, proposed a radical interpretation. The entropy of a black hole measures the information content of everything that has fallen into it. And this information is stored not in the three-dimensional volume, but on the two-dimensional event horizon. The black hole's interior might not contain independent degrees of freedom at all. Everything happening inside could be completely described by data encoded on the surface. If this is true for black holes, maybe it's true everywhere. Perhaps all three-dimensional volumes are fundamentally described by information on their boundaries. Our three-dimensional universe, with its depth and volume and space, might emerge from a two-dimensional description, like a hologram where a two-dimensional film contains enough information to create a three-dimensional image. This is the holographic principle. The idea received stunning support from string theory in 1997, when Juan Maldacena discovered the ADS/CFT correspondence. ADS stands for anti-Sitter space, a particular solution to Einstein's equations with negative cosmological constant. It has some unusual properties. Space curves in a way that any point near the boundary is infinitely far from the center in a specific sense. CFT stands for conformal field theory, a quantum field theory with special symmetries that lives on the boundary of the ADS space. Maldacena showed that these two descriptions are equivalent, Every statement about physics in the gravitational theory living in the bulk of ADS space corresponds to a statement about the non-gravitational quantum field theory on the boundary. Gravity in 3 spatial dimensions emerges from a quantum theory in 2 spatial dimensions. This wasn't just a metaphor or an approximation. It was an exact mathematical equivalence, a duality. The 3-dimensional gravitational theory and the 2-dimensional quantum theory are 2 different ways of describing the same underlying physics. This correspondence provided the first concrete realization of the holographic principle. It showed, at least in this special case, that a volume really can be described by data on its boundary. Black holes in the ADS space correspond to thermal states in the boundary theory. Hawking radiation and black hole evaporation correspond to thermalization processes in the boundary quantum system. The information paradox finds a natural resolution. Information never enters the black hole in the fundamental description because the fundamental description doesn't have an interior. It only has the boundary theory. Now, our universe doesn't have the geometry of ADS space. We live in a space with positive or zero cosmological constant, expanding according to different rules. But physicists have developed analogous holographic descriptions for more realistic cosmologies, including de Sitter space, which resembles our accelerating universe. These de Sitter holographies suggest that our observable universe might be described by quantum information encoded on the cosmological horizon, the boundary beyond which we cannot see due to cosmic expansion. For black holes specifically, holography suggests that the interior isn't fundamentally real in the way we usually think. When matter falls toward a black hole, 2 descriptions remain valid. From the perspective of an outside observer, using the boundary description, the infalling matter never truly enters the black hole. It appears to freeze at the horizon, its information spreading across the event horizon, where it becomes encoded in the area. From the perspective of the infalling matter itself, using the interior description, it crosses the horizon and continues falling toward the singularity. Both descriptions are valid, both are real, but they're complementary. You can use one or the other, but not both simultaneously. This is called black hole complementarity. This complementarity might seem like a cheat, having 2 contradictory descriptions both be correct. But it's not unique to black holes. Quantum mechanics already has complementarity built in through the Heisenberg uncertainty principle. You can measure a particle's position, or you can measure its momentum, but you cannot measure both simultaneously with arbitrary precision. Complementarity in black holes extends this quantum principle to the structure of space-time itself. The holographic principle has profound implications for understanding black holes as gateways. If the interior of a black hole is encoded on its surface, then the interior might not be a separate physical space in the conventional sense. It might be an emergent phenomenon, a way of organizing information that appears 3-dimensional from certain perspectives, but is fundamentally 2-dimensional. And if this is true, then the connections between black hole interiors and other regions, whether within our universe or to other universes, might also be encoded holographically. Consider the ER equals EPR conjecture we mentioned earlier. This proposal suggests that quantum entanglement and Einstein-Rosen bridges are the same phenomenon viewed from different perspectives. In a holographic framework, this connection becomes even more natural. Quantum entanglement is a relationship between quantum bits of information. If space-time emerges from patterns of quantum information, as holography suggests, then entanglement patterns quite literally create space-time geometry. 2 entangled systems aren't just correlated through some mysterious action at a distance. They're connected by a geometric structure, a wormhole at the quantum level that emerges from their shared information. Brian Swingle and Mark van Ramsdonk have developed this idea further showing how entanglement patterns in boundary quantum theories produce connected geometric structures in the bulk spacetime. When two regions of the boundary theory become entangled, a spatial connection appears between the corresponding regions in the bulk. Increase the entanglement, and the connection becomes stronger, the wormhole wider. Break the entanglement, and the geometric connection severes. Space itself, in this picture, is woven from quantum entanglement. This has radical implications for how we think about black holes connecting to other universes. In a holographic framework, other universes might not be distant places in some higher dimensional space. They might be different boundary descriptions, different quantum systems, whose entanglement patterns with our system create geometric connections in emergent bulk spacetimes. A black hole serving as a gateway wouldn't involve physically traveling through space to reach another location. It would involve transitioning from one holographic description to another, from one boundary theory to its dual. The mathematics becomes abstract here, difficult to visualize in conventional terms, but the central idea is clear. Holography tells us that space-time geometry isn't fundamental. Information is fundamental. Geometry emerges from how that information is organized and correlated. And black holes, being regions of extreme space-time curvature, correspond to special patterns of information organization, where the usual relationships between bulk and boundary, between interior and exterior, become ambiguous or multiply-defined. Some physicists have speculated that passing through a black hole's event horizon might be like undergoing a holographic transformation. From our perspective, in the bulk spacetime, you enter the black hole and fall toward the singularity. But there might be a dual description where you transition to a different boundary theory, experiencing what appears from your perspective like emergence into a different spacetime, a different universe. The mathematics doesn't yet rigorously establish this possibility, but it opens conceptual doors that didn't exist before holography. The holographic principle also connects to the information paradox resolution we discussed. If black hole interiors are encoded on event horizons, and if Hawking radiation gradually carries away the information from those horizons, then information never actually enters an interior from which it cannot escape. It gets scrambled and encoded in the radiation through the holographic dictionary that relates bulk physics to boundary physics. The appearance of an interior from this viewpoint is an illusion created by using the wrong description. The fundamental description is the boundary theory, and in that theory, information clearly escapes. Yet from the perspective of an infalling observer, the interior feels completely real. They experience falling through space, approaching the singularity, measuring local physics that looks three-dimensional. This isn't an illusion in the sense of being false. It's an emergent phenomenon, real within its context, but not fundamental to the deepest description of reality. It's like asking whether the characters in a video game are real. Within the game's logic, they're real. They interact, have properties, follow rules. But at a deeper level, they're patterns of bits in computer memory. Both descriptions capture truth, but they're not at the same level. Holography thus provides yet another framework for thinking about black holes and the multiverse. Instead of extra spatial dimensions or eternal inflation creating separate universes, holography suggests that multiple descriptions, multiple quantum theories living on different boundaries, might all be equally valid descriptions of related or interconnected bulk geometries. Black holes, being regions where bulk geometry becomes extreme, might represent points where these different descriptions connect, overlap, or transition into one another. The experimental accessibility of holographic ideas remains limited. We cannot directly probe the event horizon of a black hole to see how information is encoded. We cannot verify that our universe has a holographic description by somehow accessing its boundary. But indirect tests are possible. The correspondence predicts relationships between quantities in gravitational physics and quantities in quantum field theories that can be calculated and compared. The mathematics has proven robust and internally consistent across thousands of research papers. And increasingly, physicists use holographic methods to make predictions about quantum systems, like quark-gluon plasmas that we can create in particle accelerators. The holographic principle represents one of the deepest insights about quantum gravity to emerge in the past 3 decades. It tells us that reality has layers of description, that geometry and information are 2 sides of a coin, and that black holes occupy a special place in this structure. Whether they serve as literal gateways to other universes remains uncertain, but they clearly serve as gateways to deeper understanding, forcing us to revise our most basic assumptions about space, time, and the nature of existence itself. While quantum mechanics and string theory provide pathways to parallel universes through branching realities or extra dimensions, cosmology offers yet another route through the process of cosmic inflation. And this inflationary multiverse might connect to black holes in unexpected ways. Cosmic inflation is the theory that the universe underwent a brief period of exponential expansion in its earliest moments, within the first fraction of a second after the Big Bang. This rapid expansion solved several puzzles about our observable universe. It explained why the universe is so uniform, with nearly identical properties in regions too far apart to have ever communicated. It explained why space is so flat, with geometry very close to Euclidean rather than curved. And it explained the origin of the density fluctuations that eventually grew into galaxies and clusters. The basic mechanism involves a quantum field called the inflaton. This field starts in a high energy state, similar to a ball perched on a hilltop. The energy density of this field acts like a cosmological constant, causing space to expand exponentially. As the field slowly rolls down its potential energy curve toward a lower energy state, the expansion continues. Eventually, the field reaches the bottom of its potential, and the inflation ends. The field's energy converts into ordinary matter and radiation through a process called reheating, and the universe transitions into the more familiar expansion described by standard Big Bang cosmology. This picture explained observations beautifully. The cosmic microwave background radiation, measured with exquisite precision by satellites like COBE, WMAP, and Planck, matched inflation's predictions for how matter should be distributed across the early universe. The theory became the standard model of early universe cosmology, accepted by most physicists as the best explanation for our universe's large-scale properties. But inflation has a strange feature that some theorists noticed early on. Once inflation starts in any region of space, quantum fluctuations ensure that it will never completely stop everywhere. Imagine the inflaton field as a landscape of hills and valleys. Different regions of space have the field at different points on this landscape. Most regions eventually roll down to the valley, ending inflation locally. But quantum uncertainty means the field's value constantly fluctuates. In some regions, these fluctuations push the field up the hill rather than down, reigniting inflation in that patch. This creates a runaway process. The regions still inflating expand exponentially, growing much faster than the regions where inflation has ended. Even though inflation ends in most places, the inflating regions grow so rapidly that they quickly dominate the total volume. And within those inflating regions, quantum fluctuations create new patches where inflation continues even longer. The result is eternal inflation, a process that, once started, never completely stops. It continues forever, generating an endless hierarchy of expanding spaces. Alan Guth, André Linde, and Alexander Vilenkin developed this concept in the 1980s and 1990s. Their calculations showed that eternal inflation is likely generic. For most inflation models, if inflation happens at all, it becomes eternal. It's not a fine-tuned special case. It's the natural outcome once the process begins. The regions where inflation ends are called bubble universes. Each bubble forms when the inflaton field in some region finally rolls to the bottom of its potential and inflation ceases. Within the bubble, matter and radiation form, galaxies condense, stars ignite, planets coalesce. Each bubble becomes an observable universe like our own, expanding according to standard cosmology. But outside the bubble, eternal inflation continues, and more bubbles constantly form. These bubble universes are causally disconnected from each other. Light and signals cannot travel fast enough through the eternally inflating background to pass from one bubble to another. Each bubble expands, but the space between bubbles expands faster, driven by eternal inflation. From inside any bubble, you can only see the interior of your bubble. The other bubbles and the eternally inflating background remain forever beyond your cosmological horizon. But here's where the connection to string theory becomes crucial. Recall the string landscape, the vast space of possible configurations for the compactified extra dimensions. Different configurations produce different physical laws. André Linde and others realized that eternal inflation provides a mechanism to populate this landscape. Each bubble universe might have different compactification geometry, different physics. One bubble might have electrons heavier than in our universe. Another might have stronger electromagnetic forces. A third might have different numbers of spatial dimensions that are large enough to be observable. The combination of eternal inflation and the string landscape produces what's called the multiverse landscape. Not only are there infinitely many bubble universes, but these bubbles have diverse physical laws drawn from the possibilities allowed by string theory. Our universe is just one bubble with one particular set of physical constants and laws. Other bubbles have different constants, different particles, different forces. Some might be hospitable to complex structures and life. Others might be sterile, unable to form atoms or stars. We find ourselves in a universe compatible with our existence, not because our laws are special, but because we could only evolve in a bubble where the laws permit complexity. This multiverse scenario makes many physicists uncomfortable because it seems to abandon predictive power. If anything consistent with string theory happens somewhere in the multiverse, then the theory doesn't make specific predictions that we can test. It just says all possibilities occur. Some researchers have tried to develop measures, probability distributions over the landscape, that would let us calculate which types of universes are more common and whether our observed universe is typical. But these attempts face severe technical challenges involving infinities and ambiguities about how to count infinite sets of universes. Nevertheless, eternal inflation remains a leading model for the early universe because it's a natural consequence of inflation, which fits observations so well. And this brings us to the connection with black holes. Several physicists have noticed striking similarities between bubble universes forming in eternal inflation and black holes forming in space-time. When a region of space is inflating eternally, other regions where inflation has ended are like islands embedded in an expanding background. From inside these islands, the boundary appears like a horizon. You cannot see beyond it because the external space is expanding too fast. This cosmic horizon is similar in structure to a black hole's event horizon. Both are boundaries from which information cannot escape to reach distant observers. Lee Smolin proposed in the 1990s that black holes might spawn baby universes, new regions of space-time that bud off from black hole singularities. These baby universes would be causally disconnected from the parent universe, unreachable and unobservable. But they would exist, each potentially having slightly different physical constants inherited with mutations from the parent universe. This creates a form of cosmological natural selection, where universes producing many black holes also produce many offspring universes. potentially explaining why physical constants seem tuned for black hole formation. More recently, some theorists have explored whether the inflationary bubbles themselves might be connected to black holes in parent universes. The Big Bang of a bubble universe, from this perspective, might be the interior of a black hole in another bubble. The singularity at the start of our universe's time might be the same singularity at the center of a black hole in some other region of the eternally inflating space, or in some parent universe. This idea remains highly speculative and lacks detailed mathematical support. The geometry inside a black hole formed from collapsing matter doesn't obviously match the geometry of an inflating universe. But the conceptual connection is intriguing. Both involve extreme space-time curvature. Both involve horizons that separate causally disconnected regions. And both involve singularities where our current physics breaks down. Perhaps a more complete theory of quantum gravity would show that these seemingly different structures are related, that black hole singularities resolve into expanding spaces, that our Big Bang is the far side of a black hole elsewhere. There are also connections through the holographic principle. If our universe has a holographic description, information about it is encoded on a cosmic horizon. Similarly, information about a black hole is encoded on its event horizon. Some physicists have speculated that these might be different manifestations of the same principle, that bubble universes and black holes both represent regions of space-time whose information content is captured by horizon areas. The eternal inflation scenario thus provides another multiverse framework in which black holes might play a special role. Whether black holes literally create or connect to other bubble universes remains unknown. But the mathematical and conceptual parallels between black holes and cosmological horizons suggest deep connections that we're only beginning to understand. Both represent boundaries in space-time. Both involve extreme physics, where quantum gravity effects should dominate, and both challenge our understanding of how information and causality work in the universe. While most multiverse theories place parallel universes in space, either in extra dimensions, quantum branches, or distant bubbles, Roger Penrose has proposed that the multiverse might extend through time. His conformal cyclic cosmology suggests that our universe is just one eon in an infinite sequence, each aeon beginning with a Big Bang and ending in a vastly expanded, emptied state that somehow becomes the Big Bang of the next aeon. The idea emerged from thinking about the ultimate fate of our universe. Observations since the late 1990s have established that cosmic expansion is accelerating. A mysterious dark energy, perhaps the cosmological constant, drives this acceleration. If this continues indefinitely, the universe will expand forever, becoming increasingly cold, dark, and empty. Stars will exhaust their fuel. Stellar remnants will slowly evaporate. Black holes will gradually evaporate through Hawking radiation over incomprehensibly long timescales. Eventually, after perhaps 10 to the 100 power years or more, the universe will contain nothing but extremely dilute radiation, spreading through an ever-expanding space. Most cosmologists view this as the end of cosmic history. The universe approaches a state of maximum entropy, perfect thermal equilibrium, the ultimate heat death. Nothing interesting can ever happen again. Time becomes meaningless because there's no change, no structure, nothing to distinguish one moment from another. But Penrose noticed something interesting about this far future state. In such a universe, nothing has mass in the conventional sense. All massive particles have decayed or fallen into black holes, and the black holes have evaporated, converting their mass into radiation. Only massless particles, photons, and perhaps gravitons remain. And for massless particles, there's no meaningful notion of scale or size. A universe filled only with radiation has no natural way to measure distances or time intervals. This observation leads to a mathematical idea called conformal geometry. In conformal geometry, you ignore overall scales and focus only on angles and shapes. A small triangle and a large triangle that have the same angles are conformally equivalent. The geometry doesn't care about absolute sizes, only relative proportions. And Penrose realized that the far future of our universe, containing only radiation, can be described purely in terms of conformal geometry. Here's the remarkable step. The very early universe, just after the Big Bang, also has no natural scale. In the first infinitesimal moments, before particles acquired mass through the Higgs mechanism, everything was radiation. The physics was conformally invariant, without absolute measures of size or distance. Penrose proposed that these two seemingly different states, the infinite future of one eon and the beginning of the next aeon, are actually the same state viewed from different perspectives. The end of one universe is the Big Bang of the next. How can this work? The trick involves a conformal transformation, a mathematical operation that rescales everything. Take the infinite future of the old eon, where space has expanded to infinite size and time has stretched to infinite duration. Apply a conformal transformation that rescales this infinite state into a finite one. From the new perspective, after the transformation, what was infinitely far in space and time becomes finite. What was the heat death of the old aeon becomes the hot, dense initial state of the new aeon. This isn't meant as a temporal process where one universe causes the next. Instead, Penrose suggests that time itself continues across the transition. The mathematical structure of space-time naturally connects the end of one aeon to the beginning of the next through conformal equivalence. There's no discontinuity, no moment of creation or destruction. The cosmos simply continues, cycling through aeons, each lasting perhaps trillions upon trillions of years before transitioning to the next. But what about black holes? In the old aeon, black holes form and eventually evaporate. Their evaporation is crucial to the model. If black holes persisted forever, they would carry entropy and mass energy into the infinite future, preventing the universe from reaching a purely conformal state. Penrose's model requires that all black holes completely evaporate, leaving only radiation. However, the evaporation process leaves an imprint. The radiation, emitted as a black hole evaporates, carries information about the black hole's history encoded in quantum correlations. This information spreads through space and time. When the aeon transitions to the next aeon, this information survives the conformal transformation. It appears in the new aeon as specific patterns in the initial conditions, subtle correlations in the distribution of matter and energy. Penrose has claimed that we can detect these patterns from previous eons by carefully analyzing the cosmic microwave background radiation. He calls them Hawking points, locations in the CMB that correspond to where supermassive black holes evaporated in the previous eon. These points should show specific statistical signatures, subtle correlations in the temperature fluctuations that differ from what standard inflation predicts. Penrose and his collaborators have published papers claiming to detect these signatures in the actual CMB data from the Planck satellite. They've identified circular patterns of correlations that they argue match the predicted Hawking points. Other cosmologists have examined these claims and remain skeptical. The patterns Penrose identifies might be statistical flukes, artifacts of looking for specific features in noisy data. The mainstream view is that the CMB matches inflation's predictions well and doesn't show clear evidence for cyclic cosmology. Nevertheless, the conformal cyclic cosmology represents a bold alternative to standard cosmological models. It provides a universe without a true beginning, avoiding the puzzles about what caused the Big Bang or what existed before it. It explains the low entropy of the early universe as a consequence of the far future of the previous eon, where entropy per mass scale becomes low because there's no mass. And it gives black holes a special cosmological role, serving as bridges between aeons through their evaporation and the information they release. From the perspective of black holes as gateways, Penrose's model suggests a different kind of connection. Black holes don't lead to other universes in space. Instead, they connect to other eons in time. The information that falls into a black hole in our aeon isn't lost. It gets released through Hawking radiation, spreads through our universe, and eventually imprints itself on the initial conditions of the next aeon. In this sense, black holes serve as information highways across the boundaries of cosmic time, carrying data from old aeons to new ones. This temporal multiverse is philosophically distinct from the spatial multiverses of eternal inflation or many worlds. In eternal inflation, all the bubble universes exist simultaneously in the eternally inflating background. In many worlds, all quantum branches exist in superposition, but in Penrose's cosmology, only one eon exists at a time. The previous eon has already transitioned to ours. The next aeon hasn't started yet. The multiverse is sequential rather than parallel, yet there are connections to other ideas we've discussed. The holographic principle might explain how information survives the conformal transformation between eons. If the late-time universe has a holographic description, and if the early-time universe also has a holographic description, then the transition between eons could be understood as a transformation between different holographic frameworks. The black hole's role in this transition becomes a story about how information encoded on horizons gets transformed and transferred across the cosmic transition. Penrose's model also connects to ideas about time and causality in general relativity. The conformal transformation that links eons is similar in spirit to the transformations used in Penrose diagrams, the tools Roger Penrose himself invented to study black hole geometry. Just as Penrose diagrams help us visualize the entire structure of a black hole spacetime by conformally compressing infinite regions into finite diagrams, the conformal cyclic cosmology conformally connects infinite cosmic futures to finite cosmic beginnings. Whether Penrose's specific model is correct remains an open question. The evidence from the CMB is ambiguous at best, and many features of the model need more detailed development. But the general idea that our universe might be part of a larger temporal structure, that black holes might serve as information carriers across cosmic transitions, and that the end of one universe could become the beginning of another, all represent fascinating possibilities that challenge conventional cosmological thinking. We've explored multiple pathways through theoretical physics, each suggesting different ways that black holes might connect to other universes or serve as gateways to regions beyond our observable cosmos. Now we must ask, what does the totality of this evidence tell us? Are black holes really gateways? And if so, in what sense? Let's synthesize what we've learned. General relativity's mathematical solutions contain Einstein-Rosen bridges, wormholes connecting distant regions of spacetime. These structures appear naturally in the equations, but they're not traversable without exotic matter, and they probably don't exist in black holes formed from real stellar collapse. However, the fact that the mathematics includes them at all tells us that spacetime has more flexibility than we might naively assume. Connections through space, shortcuts that bypass intervening distances, are possible within the laws of physics, even if nature doesn't commonly realize them. The many worlds. Interpretation of quantum mechanics suggests that reality constantly branches, creating parallel universes with every quantum event. Black holes, as quantum objects despite their macroscopic size, participate in this branching. Each black hole exists in superposition across countless quantum branches, slightly different in each. The interior of a black hole might represent a region where quantum branches have unusual topology, where the branching structure differs from the rest of spacetime. Crossing the event horizon might involve transitioning between branches in ways we don't yet understand. String theory and brane cosmology propose extra dimensions beyond the three of space we perceive. Our universe might exist on a three-dimensional brane, floating in higher dimensional space, with other brane universes nearby in dimensions we cannot access. Black holes, which warp the observable dimensions dramatically, likely warp the extra dimensions as well. They might create structures connecting different branes, serving as bridges between our universe brane and others. The holographic principle reveals that space-time geometry emerges from information patterns, that three-dimensional space might be encoded on two-dimensional surfaces. Black hole interiors, in this framework, aren't fundamental. They're emergent descriptions of information encoded on event horizons. The connections between black holes and other regions, whether in our universe or beyond, might be information theoretic rather than geometric, patterns of quantum entanglement that create the appearance of spatial connection. Eternal inflation populates the cosmos with countless bubble universes, each causally disconnected from the others. These bubbles might have different physical laws drawn from the string landscape. Black holes and bubble universes share structural similarities. Both involve horizons, extreme curvature, and singularities where our current physics fails. Some theoretical work suggests these structures might be related, that black hole singularities might resolve into expanding bubble universes, that our Big Bang might be the interior of a black hole in another bubble. Penrose's conformal cyclic cosmology extends the multiverse through time rather than space. Black holes serve as information carriers between eons, evaporating completely and imprinting their histories on the next cosmic cycle. The gateway here isn't spatial, but temporal. Black holes connect past eons to future ones through the information they process and release. Finally, there's the ER equals E PR conjecture, connecting Einstein-Rosen bridges to quantum entanglement. This suggests that every entangled pair of particles is connected by a microscopic wormhole, that the fabric of spacetime is laced with countless tiny connections. Black holes, which are entangled with the Hawking radiation they emit, might be connected through quantum wormholes to distant regions where their radiation has traveled. These connections might not be traversable, but they represent a kind of gateway nonetheless, a channel through which quantum information flows. What should we make of this varied landscape of ideas? Several themes emerge. First, modern physics repeatedly suggests that our observable universe isn't all there is. Whether through quantum branching, extra dimensions, eternal inflation, cyclic time, or holographic encoding, multiple frameworks point toward a reality larger and stranger than direct observation reveals. This convergence across independent theoretical approaches gives weight to the general concept of a multiverse, even if the specific mechanisms remain uncertain. Second, black holes occupy special positions in all these frameworks. They're regions where spacetime becomes extreme, where quantum effects and gravitational effects both become strong, where information and geometry interact in unusual ways. They're natural laboratories for physics beyond our everyday experience, and natural candidates for structures that might access or connect to the larger reality beyond our universe. Third, the connections, if they exist, are subtle and probably not practically traversable. Even if black holes contain wormholes or connect to other universes through extra dimensions or quantum entanglement, actually using these connections would face enormous obstacles. The forces involved would destroy any complex structure attempting the passage. The timescales might be wrong. You might not survive long enough inside a black hole to reach any gateway before the singularity destroys you. The quantum information channels might not permit classical information transfer. The causal structure might forbid signaling or communication. This means that even if black holes are gateways in principle, they're probably not usable gateways for beings like us. We cannot travel through them to explore other universes. We cannot send messages through them to make contact with intelligences that might exist in parallel realities. The gateways, if real, are theoretical rather than practical, accessible to mathematics but not to spacecraft. Yet, there's a fourth theme that might offer hope. Our current understanding is incomplete. General relativity and quantum mechanics are both provisional theories, extraordinarily successful within their domains, but incompatible with each other at the deepest level. We lack a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches attempt to provide this theory, but none has yet achieved consensus acceptance or experimental verification. When we finally understand quantum gravity, the picture might change dramatically. The singularity at the center of a black hole is where our current theories break down. We cannot describe what happens there using general relativity or quantum mechanics separately. A complete quantum gravity theory would resolve the singularity, replacing the infinite curvature with something finite and comprehensible. And this resolution might reveal structures we cannot currently imagine. The singularity might resolve into a bounce that creates a new expanding region of space-time. It might resolve into a connection to a different sheet of reality. It might dissolve into a quantum foam of microscopic space-time fluctuations that contains information channels to other domains. We simply don't know. The interior of a black hole beyond the event horizon represents territory that our current maps cannot chart. Until we have quantum gravity, we're extrapolating, guessing, working with mathematical structures that might not correspond to physical reality. The various multiverse frameworks we've discussed are our best attempts to extend known physics into unknown regimes, but they remain tentative and incomplete. There's also a deeper philosophical question lurking here. What does it mean for black holes to be gateways if we can never verify this experimentally? If no signal can return from beyond the event horizon, if no observation can confirm what lies inside, if no experiment can test whether connections to other universes exist, then in what sense is the question scientific? Isn't science supposed to be about testable predictions, falsifiable hypotheses, empirical verification? This is a legitimate concern that many physicists share. Some argue that multiverse theories are metaphysics rather than physics, interesting philosophical speculation, but not proper science because they make no testable predictions. Others respond that the multiverse emerges from theories that do make testable predictions. We test inflation, quantum mechanics, and general relativity. These theories, tested and confirmed in accessible regimes, make statements about what lies beyond our observational horizons. If we trust the theories where we can test them, we should accept their implications even where we cannot test them. The debate continues, but regardless of whether we can ever directly observe other universes or probe the interior of a black hole, the theoretical exploration remains valuable. It pushes the boundaries of our understanding, reveals connections between different areas of physics, and challenges our assumptions about the nature of reality. Even if purely theoretical, the question illuminates the structure of our most fundamental theories. Future directions, where research leads next. The question of whether black holes serve as gateways to other universes remains open, but research continues along multiple promising directions. Several experimental and observational programs might provide indirect evidence for or against various multiverse scenarios. And theoretical work continues to refine our understanding of black holes, quantum gravity, and the structure of reality. One of the most exciting frontiers involves gravitational wave astronomy. The detection of gravitational waves from merging black holes by LIGO in 2015 opened a new window onto the universe. These ripples in space-time carry information about the most violent events in the cosmos, colliding black holes, merging neutron stars, and possibly more exotic phenomena we haven't yet observed. As detectors become more sensitive and more numerous, we'll observe thousands of black hole mergers across cosmic history. These observations test general relativity in the strongest gravitational fields we can access. So far, the observations match Einstein's theory perfectly. But if extra dimensions exist, if black holes have unusual interior structures, if quantum gravity effects modify general relativity in extreme conditions, these might leave subtle signatures in gravitational wave patterns. Researchers are developing sophisticated techniques to look for these deviations, echoes in the waveform that might indicate structure near the event horizon, anomalies in the ring-down phase as the merged black hole settles into equilibrium, or unexpected polarization patterns that might reveal extra dimensions. Future gravitational wave detectors will push further. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will observe gravitational waves at lower frequencies than ground-based detectors can reach. This will allow it to detect supermassive black hole mergers, billions of light years away, probing black holes millions or billions of times more massive than those LIGO observes. The Einstein Telescope and Cosmic Explorer, next-generation ground-based detectors, currently in the design phase, will have 10 times the sensitivity of current instruments, detecting waves from across the observable universe. These observations might reveal whether black hole horizons have the smooth, structureless character that general relativity predicts, or whether quantum effects create additional features. Some theories suggest that quantum corrections pile up near the horizon, creating observable deviations from classical predictions. Other theories propose that the interior structure affects how black holes merge and ring down. Detailed observations of many mergers across different mass ranges and cosmic epochs will test these predictions. Another frontier involves the Event Horizon Telescope and future instruments for imaging black holes directly. The 2019 image of the supermassive black hole in Messier 87 was a triumph, showing the shadow cast by the event horizon surrounded by glowing accretion disk material. The subsequent image of Sagittarius, a star at the Milky Way's center, confirmed that supermassive black holes exist and that they have the properties general relativity predicts. But those early images were relatively crude, showing overall structure but limited detail. The next generation of radio telescope arrays will provide higher resolution, potentially revealing fine structure in the photon ring, the circular pattern of light bent around the black hole by strong gravitational lensing. This photon ring encodes information about the space-time geometry near the horizon. If the black hole has unusual properties, charge, extreme spin, or modifications from quantum gravity, these should affect the photon ring's detailed shape. Observations of multiple images of the same black hole over time might reveal changes in the accretion flow, the rotation of the hole, or variability that tests our models. Studying many different black holes, comparing their properties across mass ranges and environments, will help determine whether all black holes are described by the simple Kerr solution, or whether nature includes more exotic varieties. Particle physics experiments might also provide relevant evidence. If extra dimensions exist at accessible scales, the Large Hadron Collider or future colliders might produce microscopic black holes in high-energy collisions. These black holes would evaporate instantly through Hawking radiation, but their decay products would have characteristic signatures that would prove their existence. So far, no such signatures have been observed, placing constraints on extra-dimensional models. Future colliders with higher energies might push these searches further. Alternatively, observations of cosmic rays, The high-energy particles that constantly bombard Earth from space might reveal extra-dimensional effects. The highest energy cosmic rays have energies far beyond what any human-built accelerator can reach. When these particles collide with particles in Earth's atmosphere, they create cascades of secondary particles. If extra dimensions affect physics at high energies, the properties of these cascades might differ from standard predictions. Observatories like the Pierre Auger Observatory study these cosmic ray air showers, looking for anomalies that might hint at new physics. On the theoretical side, quantum gravity research continues to advance. String theory has made substantial progress in understanding black hole microstates, the quantum configurations that give rise to black hole entropy. By counting these microstates in special cases, string theorists have reproduced the Bekenstein-Hawking entropy formula from first principles, a major triumph for the theory. Extending these calculations to more realistic black holes remains a major research program. Success would provide strong evidence that string theory correctly describes quantum gravity and would shed light on what black hole interiors really contain. Loop quantum gravity, an alternative approach to quantizing gravity, has also made progress. This framework treats spacetime as woven from quantum threads, discrete loops of space that connect at nodes. In loop quantum gravity, black hole singularities don't exist. Instead, the extreme curvature at the classical singularity is resolved by quantum effects, and the geometry bounces, potentially creating a new expanding region on the other side. Some calculations suggest that this bounce creates a white hole in the future or in a separate region of spacetime. If loop quantum gravity is correct, black holes might indeed be gateways in a precise sense. You could enter a black hole, pass through the quantum bounce where the singularity would be, and emerge from a white hole into a different region, or a baby universe. Numerical simulations are increasingly important for exploring these questions. Powerful computers can solve Einstein's equations numerically for complex situations that don't have analytic solutions. Simulating what happens when matter collapses to form a black hole, tracking the interior geometry, and the formation of singularities helps us understand whether wormholes or other exotic structures might naturally arise. As computing power increases and algorithms improve, these simulations include more physics, quantum fields on curved spacetimes, accretion disk dynamics, magnetic fields, and eventually, perhaps, quantum gravity corrections. Research on the information paradox continues to yield insights. The recent progress using holography and the replica trick to calculate entropy in quantum gravity represents a major breakthrough. This work showed that information does escape from black holes through subtle correlations in Hawking radiation, resolving the paradox without violating quantum mechanics or general relativity. But many details remain to be understood. How exactly does the information get encoded in the radiation? What's the precise mechanism? How does this process connect to black hole interiors and the experience of infalling observers? Some researchers are exploring whether quantum error correction codes might explain black hole information processing. In quantum computing, error correction codes protect information from decoherence by distributing it redundantly across multiple physical qubits. If black holes use similar encoding schemes, information falling into them might be stored in a distributed way that makes it impossible to extract locally, but allows it to be recovered from the complete Hawking radiation. This would explain both why local observers experience information loss and why global observers can recover information. The ADS/CFT correspondence continues to be a tool for understanding quantum gravity. While the correspondence is best understood for anti-de Sitter spacetimes that don't describe our universe, researchers are working to extend it to more realistic geometries. Understanding holography for de Sitter space, which resembles our accelerating universe, would provide insights into cosmological horizons, and might reveal connections between different bubble universes in eternal inflation. Understanding holography for flat spacetime would help us describe quantum gravity in asymptotically flat regions, like those around isolated black holes. Quantum information theory has become increasingly important in theoretical physics. The recognition that information, entanglement, and quantum correlations play fundamental roles in spacetime structure has transformed how physicists approach quantum gravity. Tools from quantum computing and quantum information processing are being applied to problems about black holes, wormholes, and cosmology. This interdisciplinary approach might provide the breakthroughs needed to finally understand quantum gravity. Observationally, several searches might provide evidence for or against multiverse scenarios. The cosmic microwave background radiation has been mapped in exquisite detail, but future observations might reveal additional subtle signatures. Some inflationary models predict specific patterns of primordial gravitational waves that would appear as curl patterns in the CMB polarization. Detecting these patterns would confirm inflation and provide information about the energy scale at which it occurred, constraining multiverse models. Searches for cosmic strings, topological defects that some theories predict should form during cosmic phase transitions, continue. These strings would create distinctive patterns in the CMB and might be detectable with sufficient precision. Finding them would provide evidence for specific inflation models and phase transitions in the early universe. Not finding them rules out certain scenarios. Looking for collisions between bubble universes represents another observational possibility. If our bubble universe collided with another bubble in the early universe, the collision might have left an imprint on the CMB, a circular pattern of temperature correlations in a specific direction. Several groups have searched for such patterns without finding convincing evidence, but the searches continue to improve. A detection would be revolutionary, providing the first direct evidence for other universes. Philosophically, the multiverse raises questions about how we should think about scientific explanation and prediction. If all possible universes exist somewhere in the multiverse, then explaining why our universe has specific properties seems impossible. We can't say our laws are special or our constants are predicted by theory. We can only say we find ourselves in a universe compatible with our existence. This anthropic reasoning troubles many scientists, but might be unavoidable if the multiverse is real. Some philosophers and physicists have proposed that we should use typicality arguments. If many universes exist, we should expect to find ourselves in a typical universe, one that's common rather than rare in the multiverse ensemble. This would allow us to make statistical predictions about what we should observe. But implementing this idea requires solving the measure problem. How do we count universes and assign probabilities when there are infinitely many? This remains a major unsolved problem in multiverse theory. The psychological and cultural impact of multiverse theories is also worth considering. If infinite parallel universes exist, containing all possible outcomes, how does this affect how we think about choice, responsibility, and meaning? If every decision branches into separate realities, where each option occurs, does it matter which choice we make? These questions touch on free will, ethics, and the nature of personal identity. While not scientific questions in the strict sense, they're unavoidable when contemplating the implications of multiverse physics. Ultimately, whether black holes are gateways to other universes might remain forever uncertain. We might develop sophisticated theories, make detailed calculations, and build beautiful mathematical frameworks that strongly suggest connections exist. But we might never achieve definitive experimental proof. The question might remain in the liminal space between physics and metaphysics, testable in principle, but not in practice, given the limitations of our position as observers confined to one region of spacetime. Yet, the pursuit remains worthwhile. Each step toward understanding black holes, quantum gravity, and the structure of reality yields insights that ripple through physics. The holographic principle, originally derived from thinking about black holes, now influences quantum field theory and quantum information science. The ADS/CFT correspondence, a tool for understanding quantum gravity, has been applied to problems in condensed matter physics and nuclear physics. The mathematical techniques developed to study wormholes and multiverse scenarios find applications in other areas of theoretical physics. Science progresses not just through definitive answers, but through refined questions, deeper understanding, and new connections between apparently disparate phenomena. The question of whether black holes are gateways exemplifies this process. Regardless of the ultimate answer, exploring the question illuminates the deepest structures of physical law and stretches our capacity to imagine possibilities beyond our immediate experience. We've journeyed through some of the most profound and challenging ideas in modern physics, from the curved space-time of general relativity to the probabilistic quantum world, from extra dimensions to holographic encoding, from eternal inflation to cyclic cosmology. We've explored multiple frameworks, suggesting that reality extends beyond our observable universe. And in each framework, black holes occupy a special place, potential gateways or connectors or information processors linking different regions, different realities, different ways of being. What can we conclude? Black holes are demonstrably real. They exist throughout the universe, from stellar remnants a few kilometers across to supermassive giants spanning regions larger than our solar system. We've detected their gravitational waves, photographed their shadows, tracked stars orbiting around them. They're not speculation or mathematical curiosities. They're concrete features of our cosmos. These black holes are also places where our understanding reaches its limits. Beyond the event horizon, we cannot observe. At the singularity, our equations fail. The interior of a black hole represents a frontier where general relativity and quantum mechanics clash, where neither theory alone suffices, where something new and unknown must take over. This unknown territory is where gateways might hide. The mathematics of our best theories suggests various possibilities: wormholes connecting distant regions, quantum branches with unusual topology, extra-dimensional bridges between branes, holographic encoding creating emergent interiors, information channels stretching across cosmic time. Each possibility emerges from extending known physics into unknown regimes, from taking our successful theories seriously and following their implications wherever they lead. Can we be certain that any of these possibilities correspond to physical reality? Number. The interior of a black hole might be simpler than these theories suggest, or it might be stranger. Quantum gravity, when we finally understand it, might reveal that black hole singularities resolve into structures we haven't imagined. Or it might show that the singularity is genuine, that space-time truly ends there, that no gateway exists because there's nowhere to gate through to. But the exploration itself has value beyond answering the specific question. In wrestling with black holes, physicists have developed new mathematical tools, discovered unexpected connections between seemingly unrelated concepts, and deepened our understanding of space, time, information, and quantum mechanics. The holographic principle, the ADS/CFT correspondence, the resolution of the information paradox, the recognition that space-time might emerge from quantum entanglement. These insights arose from taking black holes seriously and following the mathematics wherever it led. We live in a remarkable time for physics and cosmology. Observations push into regimes that were purely theoretical decades ago. Gravitational waves let us hear black holes collide. Radio telescope arrays let us see their shadows. Particle accelerators probe energy scales approaching fundamental limits. Satellite observations map the cosmos with exquisite precision. Each new observation constrains theories, rules out possibilities, and occasionally surprises us with results nobody predicted. And yet, for all this progress, the deepest questions remain open. What is the ultimate nature of space and time? How does quantum mechanics interface with gravity? Does the universe extend beyond what we can observe? Are there other universes? And if so, how many and what kind? These questions have occupied humanity's greatest minds for generations and will likely continue to challenge us for generations to come. Black holes serve as a focal point for these questions precisely because they're extreme. They take gravity to its limit, quantum fields to their breaking point, thermodynamics to its edge cases, information theory into uncharted territory. By studying black holes, we're not just learning about exotic astrophysical objects. We're probing the foundations of reality itself. Whether black holes are gateways in any practical sense, whether you could enter one and emerge somewhere else, whether they connect to other universes you could theoretically visit, remains uncertain and probably always will. The forces involved, the timescales, the quantum mechanical constraints all suggest that even if connections exist in principle, they're not traversable by beings like us or by any information we could encode or transmit. But perhaps the gateways are metaphorical rather than literal. Black holes are gateways to deeper understanding. They're places where our theories meet their limits and must evolve. They're windows into physics we cannot yet fully comprehend. They're reminders that the universe is stranger and more wonderful than our ancestors ever imagined. Standing at the edge of a black hole, metaphorically, we stand at the edge of human knowledge. Beyond that edge lies mystery, not the mystery of ignorance, but the mystery of complexity beyond current comprehension, of structures and relationships our mathematics hasn't yet captured, of phenomena for which we don't yet have language or concepts. This mystery is both humbling and exhilarating. It reminds us how much remains to discover. The multiverse, in whatever form it takes, represents the ultimate expansion of that mystery. If other universes exist, whether as quantum branches or extra-dimensional brains or inflationary bubbles or temporal aeons, then reality is vaster than we can directly observe. We're not just residents of a planet or a solar system or a galaxy or even a universe. We might be participants in a cosmos of truly cosmic scope, where our observable universe is one thread in a far greater fabric. Black holes, those most mysterious objects in our universe, might be the knots where threads connect, where our universe touches others, where the veil between realities grows thin. Or they might simply be the end of the line, places where matter and energy meet their final fate with no further story to tell. Either way, they mark boundaries, boundaries of knowledge, boundaries of physics, boundaries of comprehension. The human spirit has always been drawn to boundaries, compelled to explore what lies beyond. We've climbed mountains to see what's on the other side. We've sailed oceans to find new lands. We've rocketed into space to walk on other worlds. Now, through mathematics and imagination, we explore the ultimate boundaries, the edge of space-time itself, the threshold where one universe might meet another, the gateway that could lead to everything we haven't yet imagined. Thank you for joining me on this journey through the cosmos and beyond. If you enjoyed exploring these ideas, please like this video and subscribe to Astroverse 120 for more deep dives into the mysteries of space, time, and reality. The universe is full of wonders waiting to be discovered, and together, we'll continue exploring them. Until next time, keep looking up, keep wondering, and keep questioning. The answers might surprise us all.